Hi folks, welcome back. I hope you're all doing well. Today I come to you with a paper from the Conference on Hot Topics and Operating Systems back in 2019. And it claims that operating systems are not dead yet, even in the era of kernel bypass mechanisms. So just to set the stage a little bit, if you look at pretty much every modern general purpose operating system, their design dates from a period in time when I/O was much slower than CPU. And so you could have very expensive abstractions that take up a lot of CPU time. Things like file systems with very high level abstractions, I/O operations with lots of complexity, again, very high level abstractions. And you could get away with this because when you did an I/O, there was just so much time spent waiting for it that the CPU could keep chugging along, offering you all these high-level abstractions. But that era has now ended. If you look at modern I/O devices, whether it is cutting-edge network cards, fast SSDs, they can easily operate at a speed that can saturate modern CPUs. So this puts us in a bit of a sticky situation. If you try to use these fast I/O devices through the kernel adds a lot of overhead and you end up pretty much saturating your CPU to make the I/O go at full speed. And it is this constraint which has led in recent times to the rise of all these kernel bypass frameworks, things like DPDK or SPDK, which let an application completely bypass kernel abstractions and go straight to the network card or straight to the storage device. But if you bypass the kernel and go straight to the hardware to get the maximum performance, that naturally begs the question, well, what kind of abstractions are you using when accessing this hardware? What about all those OS abstractions that you gave up? You end up in a situation similar to the dawn of operating systems, where every operating system was written in machine language and very tightly coupled with the hardware that it ran on. So all these modern applications end up being very tightly coupled to the specifics of the hardware devices that they are accessing. And this is the central question that this paper looks at. When you bypass the kernel to get maximum performance from fast hardware, what is the role of the operating system? There are two main problems with bypassing the kernel and going straight to the hardware. The first one is that it requires a ton of engineering effort to get right. And the second big problem is that now you're so coupled to the very intricate details of that particular piece of hardware that it becomes very difficult to change your application or to port it to different hardware. And when you bypass the kernel to go directly to the hardware, sometimes you end up needing some higher level OS functionality all the same. And then you end up re-implementing that within your application. This diagram is a helpful summary of the situation. In your traditional architecture, the OS kernel mediated all access to hardware. That's well understood. In this new architecture, you have kernel bypass frameworks which let an application go directly access I/O hardware, whereas for other things that are not dependent on fast I/O, the application still uses the kernel. But there is still a gap in terms of what if you still need some higher level abstraction when directly accessing an I/O device. Things like multiplexing or sharing. It is this gap that the authors in this paper are trying to address. They're trying to come up with design principles for what is needed in an operating system in an era of all these kernel bypass mechanisms. The first principle, somewhat obviously, is that one must optimize for user-level I/O processing. When you're directly accessing the hardware from your application, you are dealing with all the I/O processing in your application rather than in the kernel. But you don't want to simply take a kernel level I/O stack and run it in user space. That kind of defeats the whole point. So what you want is an efficient I/O processing abstraction. And the authors here reiterate, like many before them, that the POSIX abstraction is too heavyweight and simply not suitable as an abstraction to put on top of very fast I/O. One disconnect is that if you look at Unix pipes, they operate on streams of data, whereas pretty much all modern fast I/O hardware operates on atomic chunks of data, a block at a time. So we need an abstraction that breaks free of POSIX and is more tailored to this kind of hardware. What the authors are proposing is an architecture that they call a DemiKernel, which splits the kernel into two broad categories of functionality: the control path and the data path. The control path is OS functionality that is not related to I/O or that is used very infrequently. You can think of it as most of the functionality of a kernel that is not super performance sensitive. Everything in the control path still stays within a traditional kernel. Then if you look at the data path, this is where all the change is happening. The data path is the one that deals with fast I/O. And on the data path, the authors propose using a library OS to implement the missing OS abstractions that you may still need. So these will get implemented in your application and run in user space rather than kernel space. This is what the architecture looks like. You still have a traditional kernel mediating access to the CPU and to the control path. The application talks to a DemiKernel system call interface. And that system call interface multiplexes between the kernel and a library operating system, which then interacts with the kernel bypass mechanism. The library operating system is what offers a thin layer of abstraction over the fast I/O device. One of the core abstractions offered by the DemiKernel is this notion of an I/O queue. And unlike POSIX, these I/O queues operate on blocks of data rather than streams of data. And the DemiKernel offers a system call interface that applications can use. For most of the control path stuff, it goes directly to a traditional kernel, but then for all the data path stuff, for all the I/O, it interfaces to a kernel bypass mechanism. One crucial difference is that all the I/O system calls now take queue descriptors, which are similar to file descriptors. And each of these DemiKernel library operating systems supports a specific accelerator, whether it is RDMA or direct to a storage device or direct to a network card and so on. And then on top of that bypass mechanism, it implements OS functionality that is missing from that specific device. So essentially, what this architecture does is add a thin layer of indirection between fast I/O hardware and very specifically tailored bypass mechanisms and your user level application. It offers a system call interface that the application can use while still getting fast access to I/O. And the main benefit of this is that your application ends up being more portable and less tied to the specific details of the I/O hardware that it is using. So that was a quick look at an architecture which allows for applications to work at a decent level of abstraction while still getting the benefits of fast I/O and kernel bypass performance. I hope you enjoyed that, and I will see you next time. Thank you very much.